Classifier, and it's presented by Jacek, Cyranka, and Alexander Georges.
Yeah.
Thanks.
So hi, my name is Jacek Cyranka. I work at University of Warsaw and startup is Lab.
Hi, I'm Alex Georges. I'm currently at Boston Consulting Group. I'll be doing the latter half of the talk. So Jacek is going to start you guys off.
So yeah, we'll present our work on mapper-based classifiers. So our motivation is the issue of adversarial examples. So this is big. This is like outline of the talk. I will start with motivation, then present our mapper, what is mapper algorithm that you already saw in a couple of talks, and then I will show how we developed mapper-based classifiers, and we'll show our experimental results. So the issue of adversarial examples. So as you know, the commonly used classifiers which are based on convolutional neural nets are really really sensitive to small perturbation of inputs, and they get easily fooled. So there are like thousands of examples you can find online, but this is like one of the common ones. So there's, let's say we have image classifier which is recognizing several different classes. So this is image of a cat, and apparently the classifier is doing a good job because it's saying it's a cat with 90% probability, and then there's some invisible perturbation added, and the same classifier outputs that this is guacamole. So this is doesn't make sense, and moreover, what is crazy is when you rotate the same image, you get correct class back again. So this shows how this is not understood. And this shows that convolutional neural networks, they don't work as humans, as we do, when we recognize images. So we want to kind of find a different way of constructing classifiers which are using different type of features. One way of looking at where are the adversarial examples coming from. So let's say this is our CNN. There's some input, and because there are like many layers, non-linear layers, the gradient with respect to the input of the last feature vector will be huge. So it means that if you add some small perturbation to the input, it will be propagated through the convolutional layers, and the difference with the original features will be increased with the corresponding feature layers, and finally the last feature layer that gets classified by dense layer is going to be very different. So we'll get some spurious output. In this case, for example, we'll get a number 9 instead of 2. Okay, so what is our approach? What is our take on that problem? So we apply the mapper algorithm. So I will briefly present, because it already appeared on several talks today. This is another example. So we have a point cloud of a hand, and then we prescribe a filter function, which is in this case projection onto X component. So we see that the values are increasing when we move from left to right, and then we split our image into overlapping intervals, and we see how many clusters, how many disconnected clusters we have in the pre-image of each interval, and we join two. So each cluster is going to be a node in the graph, and we connect two nodes with an edge if there is no empty intersection. So this can be looked as a kind of nerve complex of the point cloud. So we develop, based on the mapper algorithm, we want to develop a classifier. So the idea is as follows. So first we have our data set. We project our data set onto latent space, which can be PCA, or it can be autoencoder, it can be whatever dimensional reduction technique. And having the latent representation of our data set, we apply the mapper algorithm onto. Okay? And moreover, we don't want to apply the mapper algorithm the whole data set because it can be huge. So as usually, we split our data set into batches, and for each batch, we construct mapper graph. Okay, so we get a graph representation of each batch of data, and we can for any. So this is done for training set, okay? Because we are dealing with supervised learning. So there's training set and testing set. So we are building this graph on our training sets. And then for each training point, we can assign a one-hot representation, okay? It can happen that the training point is in the intersection of several different clusters, and then we have more ones than only one. Then there are like two. This is like a one-dimensional mapper, so there can be either one or two non-zero elements. And so we can merge this and train like a neural net classifier based on that representation. So if we have a testing point that we haven't seen before, we can apply k nearest neighbor and take the average of the representations of the neighboring, the nearest training points, and then feed it into the classifier. So that's the general idea of our algorithm. And the interpretation is that it will be more robust because for topology, the idea is that, first of all, we cannot pass a gradient through this mapper step. Okay, it's like a topological, this because of this binarization step. We cannot compute gradient, and it doesn't matter which direction we move. If the small is changed, the point should get mapped to the same value, and Alex is going to present our experimental results.
All right, thanks, Jacek. Ryan, how much time do I have left? Like 7?
8 minutes and 22 seconds.
Okay, great. So just to continue where Jacek left off, this is basically the intuition of our algorithm. So we have some high-dimensional data space. If we're working with MNIST, we basically map them to one of these graph objects. The intuition is like when they're mapped into one of these nodes, we want to basically say, oh, look, the zeros live there, the threes live here, the sevens live there, and so on and so forth. This is kind of a lie. It's not exactly what we do, but it's just to guide your intuition. So with this in mind, having this be part of your intuition, what we do is, let's say we're talking about the threes. The threes live in some high-dimensional data space. Our task is to, when we push around those number threes in the high-dimensional data, so if we perturb them with any type of noise, it can be arbitrary noise, we want them more or less to land in the same area, right? If they land more or less in the same area, then we have a robust classifier to noise. So that's the intuition. The more technical details were on the previous slide. Okay, so let's talk about the experimental results. So right now we've only implemented 3 different types of noise. Gaussian blur, Gaussian salt and pepper. And again, what we do is we operate on the points in the original data space and we add some amount of noise to them. And by some amount, we actually vary that. So if you guys can see this, let me play that again. So you see these images are changing in the first place, and then these L2 norms are changing. So what this graphic is doing is it's basically showing you how the images change as we increase the amount of perturbation on the data in the original space. So let me just play that one more time. Hopefully this goes. And again, these are the L2 norms with respect to where the data point was originally and how far we push it away. And another thing that will guide your intuition is thinking about a type of noise as a general direction of perturbation in the original space. So if my data point is right here, I can kind of think of Gaussian blur as being a perturbation roughly in like this direction, but in 784 dimensional space, whatever this direction means. And each of these are kind of a different, more or less direction in that space. And we want to build a classifier that is noise agnostic, which means it doesn't care in which direction we push that data point. We want to be able to teach a classifier that says, hey, this is the number 3 on completely unperturbed data, and then perturb that data in any single direction and have it be robust to that. So that's our task. So just like Thomas, we work with both MNIST and fashion MNIST. Here's just a non-animated version of the previous slide. so you guys can see what the fashion MNIST looks like. And one thing I will point out is that our whole procedure is discretized, so you can't really compute gradients on it. So if you wanted to actually go in and find a specific adversarial attack to our approach, it'd be much harder than finding, you know, an adversarial example for gradient-based approaches. Okay, so how much time? I just want to know how much time.
You're good on time.
Okay. All right. So here are the main results of our classifier. So let me just describe each of these axes, and then I'll describe what the curves mean. So on the x-axis is the L2 norm, so how much noise we're adding to the data points. So this specifically is for Gaussian blur for MNIST, and we're training on 10,000 data points, testing on 10,000 data points. So yeah, x-axis is L2 norm, so you can see it gets blurrier as we go right. The y-axis is what we're calling normalized accuracy. So what that means is that each of these different classifiers are going to have an initial classification accuracy. So let's say ours is 96% and then the CNN is 98%. That will kind of be a normalizing factor so that everything starts out at 1, if that makes sense. And there's a few different reasons for this. One of them is just so that we can compare them well. Another one of them is kind of comes into when you think about the bias variance trade-off and you want to measure like how well your model is extending beyond the specific mathematical structure that it learns. I'm not sure if that makes sense. But basically, if the normalized accuracy concept, like, if you're like, what are they doing right there? It's close enough to just regular accuracy. It just makes the plot a little bit nicer, is a way to think about it. Okay, the curves. What do the curves mean? Well, in the first place, this is the CNN. So if you knew nothing about this plot, you'd be like, oh, well, it dives down, that's probably bad. It turns out that it is bad. So the CNN drops down in accuracy very quickly as we increase the noise. All of these curves up here are all for the mapper classifier-based approach. We use MC, not Monte Carlo. So if there's any physicists in the room, you'd probably be very tempted to say Monte Carlo. This grouping of curves is all the mapper-based classifier. And they're only different in how we do the initial projection. So like Jacek just mentioned, and like Gunnar was talking about earlier, there's a choice when you're producing these mapper objects of how you take this high-dimensional data and project it down to a lower dimensional space. And these curves only differ in how we do that projection. So the blue happens to be PCA, and these three right here happen to be different variations of autoencoders. So we have a contractive autoencoder, deep autoencoder, variational autoencoder. The reason that we choose PCA and autoencoders is mainly heuristics. We noticed on average that those projections performed the best. So we're like, let's continue our analysis with those. We did try other types of projections. Those other types of projections, I don't know, they might have lived in somewhere in here. But on average, those types of projections performed the best and were the most robust. So that's why we use those. Okay. So, sorry for the blurriness, but this is just an extension of the results. So last slide was train on 10,000 MNIST, test on 10,000 MNIST. Here is train on 60,000 MNIST, test on 10,000 MNIST. So just different, like how much training data we give it. This is for all the three different types of noise. So Gaussian blur, Gaussian salt and pepper. And let me go to the next one. So this is for fashion MNIST. And by the way, so the CNN is red. So notice how, again, it's lower than the mapper classifiers. So that's one takeaway here. The other takeaway is that when you hit the end of these regions, the mapper classifiers have a much smaller slope. So that you would expect, if you continue out this probing region, these would get much better and better as you go on, basically, because of the slope. So those are two takeaways. And then all in all, if you look at these results, the results that were just previously, and then the other results that we've looked at, it turns out that if we're comparing the mapper-based classifiers to the CNN, the PCA-based mapper classifier is always better than the CNN, and it's typically always much better. So, that versus that kind of thing. The mapper-based approach is noise agnostic. So remember when we were talking about you have a data point in some high-dimensional space, you want to make sure that whatever direction you perturb it your classifier does not care. That more or less turns out to be the case, and we have the theorem to show that. The slope we talked about, and we have some general ideas on why the mapper classifier might be good for certain types of noise, and much better than the CNN. We don't have to go into that right now. The last thing that I'll talk about is that when we did this whole analysis, we did not really do an exhaustive hyperparameter search. It was kind of heuristic based. We kind of fiddled around with some things, thought what might be good. So I think the next slide is future directions. So one of the big things is to perform a hyperparameter optimization for what we have, just to, like a grid search or whatever, something smarter than what we've done. Give me one more minute.
Yeah, take another.
The second thing is to implement a scalable version of our software. We do have this software posted somewhere. It's not very scalable. Third, we want to test on more data sets, basically. And thank you for listening. Thank you, Ryan and Juan.
We have time for a couple questions. We're running a little bit fast, so we can take a couple. Let me start in the front with Ryan. I'll come back.
Yeah, just out of sheer curiosity, your initial accuracies, not the normalized accuracies for the mapper-based approach, where were they falling?
So if you're talking about 60,000 train, let's say around 97% versus the CNN that we had 98-ish%. So pretty much the same. If you were,
Yeah, but it's trade-off, yeah. I mean, you get more robustness.
You sacrifice just a tiny bit of initial accuracy for extreme robustness.
Okay. We know, but before we have a parameter optimization, we think that we can boost higher this accuracy still.
Sure. Yeah. And we have another question in the back.
Yeah, so you compared your approach was designed for essentially being against adversarial examples versus a standard CNN, which would be shown in literature to be very non-robust to adversarial examples. Did you ever compare it to an adversarially trained CNN? Or do you plan to?
Yeah, this is like future work. We haven't so far we haven't compared to adversarially trained CNN, but we have this on our agenda.
I mean, would that require you train in adversarial examples for your approach as well?
No.
Like
I mean,
apples to apples comparison.
Yeah, but it's hard to say what are adversarial examples for our approach, yeah, because the Graham-based methods doesn't work, yeah. So only some some black box attack. Yeah.
I have one more question in the back, and then one last one up front, and that'll be.
I think a previous speaker had mentioned training on MNIST and comparing it to house numbers.
Comparing it to what?
House number data sets.
Uh-huh.
I was wondering, I know this is trained for adversarial approaches, but given the noise and robustness, do you think it would perform better than average CNN?
On what?
On training on MNIST and testing on house numbers.
We would need to test it.
It's my intuition that it would, just because what we're trying to do is allow some stretchiness in the main issue in my mind with the CNN is it learns the mathematical structure initially way too well, and then that just kills all future generalization. Whereas in our approach, we learn the initial structure a little bit less well, but you gain a lot of flexibility. So I think it would extend well, but yeah, something to test.
We have one more question.
Okay, actually, so when you are showing the last result of comparison with, I guess, the fashion MNIST, remember so the first one is Gaussian and the slope, when you are talking about when you are increasing the perturbation, the slope for this mapper classifier is not that much compared to the other approach. But the first one, when you are using Gaussian, your slope was pretty high. When you are closing to the maximum perturbation, it was falling very quickly. So do you know why Gaussian was like that bad?
That is something that we want to investigate more, just basically how specific types of noise specifically interacts with what we're doing and what other things are doing. I think our intuition at this point is that if you have a more global type of noise, the CNN gets worse much quicker. By global, if you have a Gaussian, the convolution, the Gauss blur that we're talking about, it's much more of a global perturbation, if you will. It doesn't operate locally. It takes into account information from the rest of the image. And we think, for whatever reason, that if it's a more global perturbation, our method will much further outperform the CNN. but something to be investigated.
Yeah, but it was not the case for fashion enemies for some reason. For fashion enemies, the behavior was the worst of CNN was for Gaussian noise, and it was like the slope was really drastically decreasing, and our method was stay higher. So.
Well, thanks a lot for the questions. Thank you. I have a question, but I'm going to wait till later, so maybe we'll make some time to meet and talk.